Hello, it's Keith here, and this is lesson 4 of my 6502 assembly programming tutorials. Now, we've been looking at the last few weeks at various commands on the 6502. We've done a few bits of mathematics and some jumps and things, but we've really been overlooking a lot of programming commands that we're going to need to actually start writing serious programs. So I want to go into detail this week about the stacks and some more mathematical commands. Now, what is a stack? Now, the 6502, like most processors, uses a stack as a temporary store. Now, on the 6502 we have the 0 page, and this allows us to store data in a logical manner, but there will be times where we need to store data while we do a new calculation and then get that same piece of data back immediately. And for this we use something called the stack. Now, when you think of a stack, I suggest you think of an in tray in your office, and if you've got an in tray and some pieces of paper, what you will do with your in tray is you might put each piece of paper into the in tray. But if you think of the in tray and imagine you can't take pieces of paper from the middle of the pile, you can only take them back off from the top, then the order you take them out will be the last one that you put in will be taken off first, and that's the way the stack works on the 6502. It's known as a last in, first out stack. So, well, what is the stack? Well, the firmware has a stack pointer. This is at memory address hexadecimal 01FF, and it goes downwards. So every time we put something on the stack pointer goes down. But we don't really need to worry about that at this stage. What we do need to worry about is how the actual stack works. So let's imagine we're using a stack with this visual example here. So if you imagine our stack currently has the values 0 and 11 on it in hexadecimal, and then we have another item we want to put onto the stack, hexadecimal 22, then we put this onto the stack, and then it appears above the two existing items on the stack. Then we add hexadecimal 33, and that goes onto the top of the stack as well, above the 22 and the two items that were on it before. Now, when we come to take an item off the stack, we get the last item that we put onto the stack. So the first item removed will be the hexadecimal 33 we put on here, and then the next item removed will be the hexadecimal 22 we put on here. So that's how the stack works. Now, we're going to see some examples of this to make it really clear to you what's going on. So don't worry if you're a bit confused at the moment, but that's just the basics of what the concept of the stack is. Now, the 6502 has a very limited set of commands that we have available to us with regards to controlling the stack. On most systems like the Z80 and the 68000, we would have a large number of commands for storing the various registers. For example, on the Z80, we can push AF for the accumulator and the flags, or BC for the B and C registers, and so on. But on the 6502, we only have a very small number of commands. All we can do is push the accumulator onto the stack, or pull the accumulator off the stack, or alternatively, we can push the flags onto the stack. Now, the flags, of course, are the things we do with comparisons. So when we do a compare command, the C and Z flag will be set or cleared, and we can actually back those up and restore them later if we need to do the compare at one point and the branch at another point. So we have this PHP, which is for pushing the processor flags, and PLP for pulling the processor flags. And these are putting the flags onto or taking them off the stack. Unfortunately, though, we might want to push X and Y onto the stack if we need to use them for a short loop or for some kind of mathematical calculation. Unfortunately, the 6502 doesn't offer us any commands to push X and Y onto the stack. So what we have to do is use TXA, which transfers the X register to the A register, and then push the A register onto the stack. And for the reverse procedure, pull A off the stack and transfer A to X. And we can do the same with Y here. Of course, the very clear problem with that is that will alter the accumulator. So if you want to push A, X and Y onto the stack, you have to push A on first, then X and Y, and if you pull them off, you would pull off A last. But that's just something we do have to deal with. Now, if you want to alter the stack pointer, you can do this by transferring the stack pointer, which is marked as S here, to X, and you can transfer X to S. So if you want to set the stack pointer to a strange value, you can do that. However, of course, on the 6502, the stack pointer is always between hexadecimal 100 and 1FF. There's no way of putting it in other positions. On the 68000 and the Z80, that is possible. But on the 6502, it's only an 8-bit pointer, so it can't do that. So I can't say that's going to be a command you're going to need very often. It probably just when you're setting up your processor, if you're working on a system like the NES or something like that. Now, on the 6502, the commands are push and pull, but on the Z80, they were referred to as push and pop. So I often refer to removing a byte from the stack as popping it off, because that's kind of how it appears because that's how I kind of imagine it in my head. So just bear with me with that. So we're going to do an example with our stack now, and let's have a look at it. So here's the example we're going to be doing, and we are actually going to load X with the value hexadecimal FF here, 255, and then we're going to transfer X to the stack pointer, just so that we've got a very simplistic stack that we can look at and understand very clearly. And then what we're going to do is we're going to load A, X and Y with some values here. We're going to push these onto the stack, pushing A on first as I described. Then we're going to transfer X to A and push A on again. Effectively this is pushing X onto the stack. Then we're going to transfer Y to A and push that on, effectively pushing Y onto the stack. Then we're going to dump the memory address hexadecimal 1FO onto the screen. This is because this is going to be the range used by the stack. So we'll see what the stack has actually done on screen. Then we're going to clear all of the registers just as a test. Then we're going to restore all of the registers back off the stack. So if you imagine this was some temporary commands we needed to do, and then these are the commands getting back the original values of A, X and Y here. And then we'll show the monitor here just so we can confirm the values have really been restored. So there we go, let's try it out. So here you can see I've run this example on a Nintendo NES, and what's the result we've got? Well, when the program ended here, you can see the stack was at hexadecimal FF, which is 255. Of course, the stack is always at 01 FF, so it would have been there. But the more important thing we want to see is the content of the registers. Now you can see A is 77, X is 66, and Y is 55, which is exactly as they started. So these pushes here and these pulls here have indeed successfully backed up and restored the stack, because we reset all of those registers just here. So that's worked fine. Now, if you look at the order that these are in, you'll see that we pushed A on first, hexadecimal 77, and that's appeared here. Now, when we push an item on the stack pointer moves down. So the next item pushed onto the stack is hexadecimal 66, and that has gone here. And then we pushed Y onto the stack here, hexadecimal 55, and that's gone onto here. Now, even though we've pulled all of these off the stack and then called the monitor here, the items that are removed from the stack aren't actually cleared. All that happens is the stack pointer goes back up. So the stack pointer is back at FF, which is here within this memory range. So while the stack pointer is no longer pointing to any of those items, the items are actually still in memory, but that doesn't make any difference. Now, just to prove a point, let's make some changes to this program. Let's put another monitor in here, and let's actually swap around the A and the Y here. So now we're pulling X and Y off in the opposite order. Well, what's going to happen now? Well, here you can see I've added an extra monitor here just so we can see what's going on a bit more clearly. And also, of course, I've swapped these two around. Now, the thing you should notice here is that X is now hexadecimal 55, which was previously the value of Y, and Y is now hexadecimal 66, which is previously the value of X. That's because when we pull items off the stack and that we pushed on before, the stack commands don't know what registers they're supposed to be pulling off. So we can pull off into a different register the value that we pushed on from another register, and that will happen intentionally or accidentally, whether we want it or not. So if we want, we can do this to transfer values between registers, but it could be a negative thing. As well as that, I want you to just take a look at the stack pointer value here. You'll see here it's FC, and that's after we'd pushed the items on the stack. So that will be just here. When we popped those items off the stack again, it went back up to FF, which will be here. So you can see every time we push onto the stack pointer goes down here, and every time we pull it off, it goes back up. And that's how the stack works. Now, on the 6502, the stack pointer is always in this hexadecimal 0100 to 01FF range. It's very limited compared to the other systems, and that means you don't really have to worry about it and necessarily understand how it works quite as much as on some of the other systems. On the Z80, it's quite important because you can actually be corrupting your program range with the stack if you really don't understand it, and you can also use the stack pointer for things like very fast data writing by manipulating its usage. But on the 6502, because it's fixed into that memory range, those aren't options for us. Now, this example should generally work on all of the systems in these tutorials, but there is an odd exception, and I'll just show it now. If I run this on the PC Engine, you'll see that this memory range is completely blank, and while it has indeed worked here with regards to restoring the registers, you can't see where the stack is. The reason for this is on the PC Engine, the stack isn't at 0100, it's at 2100. The PC Engine has a custom processor that is based on a 6502, but it is not a 6502. So just be aware that that system may work differently to how you expect. So that's how we can temporarily back up registers and restore them for later if we need to. Now we've looked at the past at the jump command, and we've seen the jump to subroutine command used for calling our monitors and things, but we've not really looked at it in detail yet. And what jump subroutine does is it moves the execution to a label where we can run a few commands, and then there'll be an RTS command which is return, and that will return from the subroutine and then carry on running commands at the previous location. And I've got an example I want to show you today that is going to make it clear how that command works in various ways. So here's an example we're going to run now. So what we're doing here is we are setting up our very simple stack pointer again. We are then calling the monitor. We're then going to push the processor flags onto the stack, and then we're going to jump to the subroutine labeled subtest. And subtest is just down here, and you can tell this is a label because it's on the far left hand side. I also put a colon on, but that's not necessary in this assembler. So when we get into subtest, what we're going to do is we're going to do a mem dump to screen of this stack area used by the processor here, and then we're going to return here. And you can see here we're also pushing A onto the stack and pulling A off the stack here as well. So we're going to have various things on the stack at this point to see in this mem dump. Now this return command here will effectively move execution back to this point here. So let's try this command out. Okay, so here we have the contents of the stack at this position here. And so what is actually on the stack? Well, the first thing we've got is the contents of the flags, which is the first thing on the stack just here, this B4 here. And you can see that is represented here. So we can see that the contents of the flags is definitely the first thing on the stack. And then also the accumulator we can see just here because we pushed that onto the stack here. But what's this thing here? Now this is a little Indian number. So it's shown as 5B10, but that's actually 105B. Well, what is that? Well, the clue you should see is here. Now this is called the program counter. This is the currently executing line of the code within the memory. And what this actually is, 105B, is it's the return address of this subroutine here. So effectively it's this command here. And why is that stored onto the stack? Well, the reason is kind of logical actually. The processor has very few registers, and the registers it does have are totally accessible to us. It's got no secret resources that it's keeping from us. So when it comes to actually doing a complex command like jumping to a subroutine and returning from that subroutine, it's having to use something that we already know about because that's really all it's got. And what it's actually doing is it's effectively pushing the last byte of the command that was just executed as part of this call onto the stack, and then when it returns here, it's popping those bytes off the stack and then incrementing them and executing the next command. So this is actually the command bytes of the return address, and that's very important for us to know because we have to match our push and pull commands, otherwise our code isn't going to work properly. Let's say I rem out this pull command here and I run this program again. Now what happened there? Well, the program actually crashed. Why did it crash? Well, we've pushed a byte onto the stack here and we didn't pull it off here. So when the return command occurred, the processor popped the next 2 bytes off the stack and returned to that memory address. One of those bytes will have been made up by that pushed on accumulator. So it's jumped to goodness knows where and done goodness knows what. We've created a mismatched stack use within this subroutine, and that's why I've indented whenever I do a push command. I indent and then remove that indent when I have the match and pull command, so that when I've got this complex combination of pushes and pulls, I make sure they match. So, well, what can we do about this? Well, obviously the most sensible thing to do is actually just to make sure we pop everything off the stack that we pushed on. But we can do other things as well. We can, for example, do a TSX here to transfer the stack to the X register, and then transfer the X register back to the stack here. Now, this will mean that even though we never popped the byte we pushed on here, the stack pointer is now pointing to the same position as it did at the start of this procedure. So now our code runs fine without crashing. Now, honestly, there's not a lot of point to that. It would have been faster to just pop the item off the stack. But the point I'm making is it is possible to do that. The other thing it's possible to do is it's possible to push an address onto the stack and then return to it, faking as if we'd actually jumped there. Let me just show you. Now, don't worry about it if you don't understand this. It's a really tricky command, and I'm not really suggesting you try it at this stage, but I just want to show you that we can actually exploit the fact that we know that the return command is popping a word off the stack and then jumping to that address. Now what I'm doing here is I'm creating a label called dodgy jump. It's going to set the accumulator to hexadecimal 32, and then it's going to call the monitor twice, and then it's going to return. Now we've jumped to this subroutine here using a JSR here, and then we're pushing the address of dodgy jump -1 onto the stack in the correct order for the processor. Now the reason we're doing -1 is because when we do a return, the 2 bytes are popped off the stack into a word, it's incremented by 1, and then that address becomes the program counter. So we need to subtract 1 for that to work, and we'll test that in a moment. And then we're showing the monitor twice here, then we're returning here, which is effectively jumping back to here, because this return will have jumped to here. Now, as I say, this is a bit of an experimental thing, but I just wanted to show you can do crazy things like this. Okay, so well, what's happened? Well, you can see we've dumped our memory here as we'd expect, but then we've clearly jumped to this subroutine here when we did this return, because the accumulator has been set to 32 and the monitor has been shown twice. Now, what about if I take this -1 off here? Well, this is going to be a little bit unpredictable. Well, what's happened? Well, the accumulator is not set to 0, but the worrying thing is we will have skipped this part of this command, but this will have been executed as bytecode, and I can't remember what command that is, but we will have unintentionally run a command there, so that's not a good idea. But as I say, I'm just showing you that if we really understand the stack at this point, we can actually exploit that understanding to allow us to do things that are maybe a little bit unconventional, but may give us a benefit when we're trying to save processing power and save memory and things. So just bear that in mind. Now we've gone into some detail on the stack there, and I think that's enough for today. But what I want to do now is discuss a bit more about numbers. Now, one thing we do have to understand within numbers in assembly is the way that positive and negative numbers work. I do have another video on my YouTube channel which goes into a lot of detail on this, and it does a lot of examples with a little program on the Z80 system. So please go and look at that if you're not too clear on the concept of negative numbers in hexadecimal. But I'm just going to give you a brief introduction now and show you a little bit about it, so hopefully that'll help you out. So the first thing to understand about negative numbers in hexadecimal and assembly is that the assembler can do a lot of the work for us. So what we're going to do is we're going to load -1 into the accumulator. Now the accumulator can only go from 0 to 255 as the other 8-bit registers. So what's going to happen there? Well, we'll see about that. Then we're going to store that into a 0-page register, which I've labelled as ZH. Now, we're going to look at those later anyway. Just bear with me on that. Then we're going to show the monitor. Then we're going to load the accumulator with 100. We're then going to add the -1 to that number. And then we're going to show the monitor again. We're going to do some other things after that, and I'm going to explain those after we've seen this example run. Okay, so we've loaded the accumulator with -1. But you can see rather strangely, the accumulator has been loaded with FF here, which is 255. Now, why has it been loaded with 255? Well, let's just have a look at what happened next. So we then loaded the accumulator with 100, and we added this 0-page register H to the accumulator, and the accumulator went down by 1. So it seems like 255 is -1 in some way. Well, what's that mean? Well, it's quite simple. A byte within a 8-bit processor can only go up to 255. So if you add another 1 to the 255, you get 0. So ironically, adding 1 is the same as subtracting 255. They're effectively the same number. 1 and -255 are the same number. And in the same way, -1 and 255 are the same number, because if you add 255 to the number 100, then you'll go up from 100 all the way up to 255, roll back to 0, and continue back up until you get to 99. So you would have effectively gone down by 1 just by adding to it. It's a bit strange, and as I say, if you don't understand it, please check that other video, or even try using the Windows calculator, because if you type in a number into the Windows calculator, you can convert them to hex, and so you can see here just how it's working with things. So the Windows calculator can help you. Also, if you're a fan of Excel, there's hex to dec commands and dec to hex commands that can help you out with this kind of thing. Please look at those if you're struggling after this tutorial. So we just saw what happened there when we added -1 to 100. Well, what about if we add 255, which is what we've done here? Well, you can see the exact same thing happened here. And I'm just reiterating the point here that the -1 isn't some magic thing. The assembler is actually converting this byte here to 255. 255 and -1 are the same number as far as the processor is concerned. So you're probably thinking, well, if 255 and -1 are the same number, how is my maths working in my game? How does the system know if I've got 255 points or -1 point? And the answer to that is it all depends how you use that code and how you use that data. If you're treating it as a positive number, a very high positive number, 255, then it's a positive number. If you're treating it as a number that's below 0, then it's a low number. And it's really just like that. You'll have an unsigned number from 0 to 255 or a signed number from -128 to +127. That's the way it really works. So how do we convert a positive number to a negative number? Let's say the user gave us a positive number and we needed to convert it to negative in some way. Well, as I say, -1 is effectively 255. And if you think of the difference between 1 and 255, this is the way you calculate it. What you do is you invert all of the bits, and we're doing that with this EOR command here. And then you add 1, and that will effectively give you the negative equivalent of a positive number. And you can see that just here, because we've taken +1 and we've converted it to FF, which is that 255 again. Now, as I say, that's possibly a bit too complex for you so far, so don't worry about it if you're confused. It's going to be one of these things that you will get more understanding of as you start playing with things. And of course, as I've said, either play with assembly like this or play with Windows Calculator, whatever helps you figure it out. Now we're going to go into two slightly abstract topics here that are very important for assembly but aren't really commands within the processor themselves, but they're things you're going to need to know, and these are conditional assembly and macros. Now, especially with 6502, because the command set is relatively limited, we will need to keep our programs small and also keep them doing things efficiently so we're not typing more than we need to. So how can we do this? Well, let's say we need a program that will compile in two different ways depending on different conditions. A very good example of this is all of my tutorials. These same tutorials can be compiled on a NES and on a BBC, on an Atari Lynx, and so on and so forth. Well, how does this happen? Well, it's simple. Different parts of the code are being switched on and off depending on what the system requires. And that's how we can compile for the BBC, or we can compile for the Atari Lynx. And the way this works is the code is switching off the different graphical routines that are needed for the different systems. So how does it do that? Well, what it does is it uses conditional compilation. And what this is where we have a command that says if defined here, and we test to see if a symbol is defined, and a symbol is defined just with a statement like this, symbol name equals, and then a number. And so if test symbol is defined, then we're going to compile this code here, and then you've got the matching end if here. And if test symbol is not defined, we're going to do this command here. So in this case, test symbol wasn't defined, and so we've done this EOR, which flips all of the bits and converts hexadecimal 1 to FE here. Well, okay, well, what about if we do define test symbol? If I just take this rem out here, we're now defining test symbol, and you can see now we've moved up to hexadecimal 2, because instead of flipping the bits, we've actually added 1. Well, what's the point of this, you're probably thinking? Well, this isn't an if statement. This isn't the processor of the resulting computer making a decision on what to do. The assembler's made the decision and compiled the code accordingly. If we have test symbol existing, this piece of code is compiled into the resulting binary, and this code doesn't exist. And if we don't define it, it's the other way around. This code exists, this doesn't. So we can have multiple different options, and the resulting file will be as small as it possibly can. If you think about it, if this program of mine here can run on 9 different 6502 systems, there's no possible way all of the code to handle the BBC version is being compiled for the NES version. It wouldn't fit in the ROM anymore, and that's what we can use it for. We can have different versions of our program or our game for different situations, different processors or different difficulty levels maybe. Maybe you want an easy version and a super hard version. You can just switch on and off different parts of the code using these compiler definitions. And that's very important when you're working in 8 bits. Now, another important thing you may want to do is you'll often have sets of commands you want to do over and over again, like these push and pull commands. And it's a real pain because we do a lot of typing, more typing, wastes our time, and it risks us making mistakes. What we can do is we can get the assembler to do all of the work for us. Let's say we want to push A, push X and push Y, and then pull A, pull X and pull Y in the opposite order. Well, we can define a macro, which is where we use a simple command and the assembler converts that to the equivalent commands and do that for us. So here we're going to create a command called push all, which is going to push all the registers on the stack, and a matching pull all, which will pop them all off the stack in the opposite order. Let's see how we can use it. So here's our first example today, and we can now take all of these out and just replace them with this push all command. And then the opposite 3 commands, we can just take all of these out and replace them with a pull all command. If we run this now, we'll see the program ran just the same. I'll just run it on the BBC as well, just so we can see it how we saw it before. So the program has executed just fine, and the benefit of this is far less typing and no risk of us getting these commands in the wrong order or anything, because we've just used a single line command. Again, now of course the important thing to understand is all of these commands do actually exist in the code as it's compiled to the resulting ROM or disk file. So we're not saving any memory using this single command. All we're doing is we're saving ourselves some typing. But when we're having to do such large numbers of commands just to push 3 registers, I think it's probably worth doing, because it will save us a lot of mistakes. Now macros do even allow us to specify parameters and use those parameters, and that's something we're going to see later on as well. So they're very complex, and if you want to know more about them, I suggest you look at the VASM documentation, the assembler I'm using, or whatever assembler you're using, because they will have different options for passing parameters. You can see here I'm passing a 0-page register, and then I'm using that 0-page address plus 1 to use a 16-bit number here, and that's something we're going to look at in just a moment. So the 6502 is a very 8-bit processor, far more 8-bit than something like the Z80. It really doesn't have any 16-bit registers at all, give or take. So how do we work with numbers that go over 255? Well, we have to start using the 0-page, and we have to start using the carry flag. We saw the carry flag before with regards to doing comparisons, but it also is set whenever we do addition and subtraction, and we can use this to do a pair of commands to work on 2 separate bytes and make up a 16-bit number. We're going to do that here, storing the 2 parts of the number in the 0-page, and what we're going to do is we're going to define some addresses in the 0-page and use them as fake registers. I tend to call them 0-page registers. Now, rather controversially, because I'm a Z80 programmer, I will name these after the Z80 registers. So we'll have H and L, which will make a 16-bit pair called HL, and we'll have BC, and that will make up a pair called BC. And I'll be referring to these with 2 definitions, an individual 8-bit definition here and a 16-bit definition here. And you'll notice the 16-bit definition points to the lower part of the 8-bit definition, and that's because the 6502 is a little endian, so the low part comes first and the high part comes second in a 16-bit number. But if you don't understand that, don't worry about it. Really what I want to say to you is, although I'm doing it in this way because this is the most logical way for me to get the 650 to work in a 16-bit way, there will be people who will feel that this is the wrong way to use the 6502 processor. If you don't like this way, if you find this confusing, I'd suggest you look for another tutorial that maybe isn't written by someone who is more naturally a Z80 programmer, because they will work in a different way and that might suit you better. But I'm pretty sure that the way I'm going to teach you will be a way that you will find easy to understand for a beginner, because when I started reading the 6502 documentation, I was really scratching my head. But when I started using these fake Z80 registers, it really started to make much more sense to me, and I found it much easier to program. So anyway, that's just a sort of disclaimer there to tell you the way I'm doing things is the way I do things. It's not the way other people may prefer to do things, but just bear that in mind. So how can we add and subtract 16-bit numbers on a system that can't do 16 bits? Well, what we need to do is we need to use some of these temporary 0-page addresses, and we can define those to be a 16-bit number, and then we can do an addition by adding the low part with the carry after clearing the carry, and then adding the high part with the carry. Now, if the low part overflowed, i.e. went over 255, the carry bit will be set. And so when we do this second add carry, that will be added to the high part so that the high part is correct. So this will effectively add 2 16-bit numbers within these 0-page registers, so to speak, and we'll store the result in one of those registers. And then this subtract command will do the same. Now we have to set the carry because the carry flag is effectively a borrow in subtraction. But again, we just do the same. We do the low part and then a subtraction on the high part, and that borrow will be transferred so that if the low part went below 0, the high part will be deducted by 1. So it's actually a lot more straightforward than we may think. And so what I've got is I've got a set of functions in this basic functions assembly file, and we can just call one of these after setting the 0-page addresses correctly, and we can just do it like that. So what's the example we're going to try here? Well, what we're going to do is we're going to set this HL0 page addresses to 1024 in hex. We're going to set DE to hexadecimal 333. Then we're going to subtract the DE pair, the 333, from the HL pair, the 1024, and then we're going to show the result here. And the result we have to show in two parts because it's two separate bytes here. So we're showing H first and then we're showing L, and we're going to show the other stages as well. So first, let's try the add command and see what happens. So you can see here, we've got 1024 here, we add 333, and we end up with 1357. Let's just confirm that's correct. 1024 plus 333 equals 1357, so that's worked correctly. Now, one interesting thing you'll notice is we have to set H and L separately because it's an 8-bit processor. It can't set both at the same time. And you'll see here we've got our normal hash, which we use to define a fixed number, an immediate value, the dollar, which is the hexadecimal number, but then we've got this greater than and we've got this less than. Well, what are these? Well, what they do is they tell the assembler, take the top byte of. So because we need to split this hexadecimal 1024 into 2 bytes, one for the high part here and one for the low part here, we need to split it in 2. So this greater than says take the high part and this less than says take the low part. So we just split that in 2 and store them in H and L. And then we do the same with the hexadecimal 333 here. Take the high part and store it in D, and then take the low part and store it in E. So that's how we can get the assembler to do the complex mathematics for us. So we saw it doing addition there. Let's try it now for subtraction. So now we've got 1024 and we've subtracted 333 and the value is CF1. So you can see that our add HLDE and our sub HLDE fake commands here do indeed work. So this is how we can do addition and subtraction in 16 bits. And of course we could go even further and extend this to 32 bits if we wanted, but it's going to get slower and slower, so maybe we don't want to. It's always important to try and keep things as simple as you can. If your game can work at 8 bits, don't use 16 bits because, you know, it's just wasting power. But anyway, there you go. That's how we can use the 0 page to allow us to do 16-bit mathematics even on our 8-bit processor. Now, there is one last thing I want to discuss with you, and that this is a real possible shocker for you as a computer programmer, and this is the fact that an 8-bit processor, or at least the 6502, can't do multiplication or division. And this is true of the Z80 as well. It's only the 6809 and the 68000 that have a multiply command, and it's only 68000 that has a divide command. So the 6502 doesn't have any of that. Now, how do we cope then? Well, there's a couple of ways we can cope, and the first one I want to discuss with you is the very simplest one, and that's just adding a value over and over again or subtracting a value. Let's have a look at the code. How can we do our multiplication and subtraction without the commands? Well, the simplest way of doing it is if we want to multiply a value, let's say we want to multiply 10 by 3, well, we can just add 10 3 times, and that will give us the effect of multiplying by 3. If we want to divide, we just repeatedly subtract, count how many times we've successfully subtracted, and that's the result. And that's exactly what we're doing here. So we're sending a value here and a counter, and we're then using this H 0 page value again. So we're storing the value we want to add into the ZH 0 page value, and then we are setting A to 0. We're repeatedly adding H, decreasing the counter each time, and then when we return, we're done. Division is almost the same. In this case, though, we're subtracting H from the value in the accumulator here, and then we are counting in X the number of times we succeeded, and then we're returning. So let's try that and see what happens. So, well, what happened here? Well, you can see here we had 0A, which is 10, and we multiplied it by 3, and then we got 1E, and what is 1E? Well, 1E is 30. So the multiplication did work here. Where you can see here we had 1F, and we divided that by 10. Well, 1F is 31, and if we divide that by 10, which is A, we get 3. But of course we have a remainder of 1. So you can see that's been represented here. Now, these are only very simple mathematical commands. The point I wanted to make to you today is that the processor does not have multiplication and division, but there are ways we can work around it, and this is a very simple one. Now, we will look at a more advanced one next time, where we will look at how to shift bits within values, which has the effect of multiplying them by 2 or dividing them by 2, and that's something you want to do quite a lot. Anyway, that's all I wanted to cover for today's lesson. I hope you've enjoyed it. Please let me know what you think of it. Anyway, thanks for watching today, and goodbye.